imagine that I have a function, I have a process, okay, that is not really, so I have a process that satisfies, for example, a stochastic differential equation. Okay? So I have xt, which is kind of representing displacement of something, it satisfies the stochastic differential equation. And then I want to know, it's not really exactly Brownian motion, so it's Brownian motion plus something else. Okay? And then I want to know that, okay, if I have a quantity that is not directly depending on Brownian motion, but on a process that depends on Brownian motion, the question is, what are going to be the dynamics of such kind of a quantity? Okay, so I'm going to start with a process that satisfies the differential equation, and then I'm going to say that, okay, imagine I have a function of not of the Brownian motion, but of the process that depends on the Brownian motion actually, and we're going to ask that what will be the dynamics of it actually. Okay? So I'll really give a heuristic derivation of it. Okay, really the proof of generalized theorem. You can find it in your in your both books, especially in this book by Kapansky. Okay, so I'll do one version of it, and then I'll prove this Ito lemma, simple Ito lemma. But the generalized Ito lemma is not, its proof is not much different from the simple Ito lemma. Okay, with a bit more, spices. By adding the spices, you can prove the generalized Ito lemma as well. Okay. So I would like to talk about now generalized Ito lemma. So what's a general Ito lemma? So general Ito lemma says that. Do you remember? We defined last time an Ito process actually. What was an Ito process? Okay. What was an Ito process? So we said that a process Ito, a process xt is Ito process. Okay. xt, okay, from either, like it's true for both, calligraphic L2AD, either you can assume this, or you can also assume that it's from L2AD, you can assume anything. Okay, so imagine that I have a process that belongs to here, satisfies the definition of L2AD. Okay. Of the form, and assume that this has following form. So this process from L2AD, L2AD of the following form. So what is the form of it? That xt can be written at any time t can be written as xa, where a is some beginning point, could be 0, could be plus integral. And you may assume that, okay, you are in this interval a to b, and t is some arbitrary instant. Okay, so xt can be written as xa plus
a to t.
Okay, a to t, a function f of s
ds.
pwfs.
Sir,
Okay, maybe
remark.
f of s ds plus. Let's call it. So I'm going to use a bit of different notations. Let's call it mu of t and u of s, u of s, w of s. Would that be a function that depends on Brownian motion? W of s. Should I say now? xs and ds plus a to t, okay, sigma of s xs pw of s, where this mu and sigma are also from L2AD, so they are processes here. Okay, they are processes here. So what's an Ito process? So Ito process is a process that contains, the Riemann integral, okay, of a process from L to AD, and a stochastic integral of a process from L to AD. Okay. So it's really in this manner. And if you're going to write it in differential form, what are you going to say? You're going to say dxt satisfies this differential equation. Mu dxt dt plus sigma dxt and so it satisfies this differential equation. So any process of this form, you're going to call it an Ito process actually. Okay. I mean, if you remember, if you see, for example, the processes, the dynamics of the processes that you have obtained in your simple and simplest Ito lemma. So one integral is Riemann integral, another is stochastic integral. So those two are really examples of Ito processes. Okay, so Ito processes. So you're going to call such kind of process an Ito process. So in other words, it's a process which has a diffusion, which has some drift and a diffusion actually. Okay. Now, for the sake of simplicity, I'm going to always write even more simple. I'm going to say that the dx is basically mu of t, could depend on xt. Okay, it's fine. Let's write it the way it is actually. Okay. So what I mean that we can write also this dxt is mu dt plus a sigma dwt. Okay. So when I'm going to do the practical calculation, I'm going to write this. But I have to, remember that there are things on which this mu and sigma, what do you call, depends. Okay. Alright. So what do we want? I want to start from here. So I want to say, suppose I have an Ito process. Suppose we have an Ito process. Okay. I have an Ito process. In other words, that process xt that satisfies say dxt equal to u of t xt dt plus sigma of dxt dwt. Okay. So I have a particle, I have an object whose dynamics can be described by this differential equation. So it satisfies this differential equation. And I want to know that I have a function f that is not now a function of Brownian motion and time, but it's a function of t and xt. Okay? And the question is, what are the dynamics of this function? You see? So I'm not saying that I have a function that directly depends on the Brownian motion, but it depends on a process that depends on Brownian motion, and I want to know what are the dynamics of such kind of process. Okay? So in order to know the dynamics of such kind of process, I'm going to give you really a heuristic argument. Okay? So let's just start with, say Taylor expansion. Okay? Let's just start with Taylor expansion. So what would be the Taylor expansion, for example, around a point? Taylor expansion, so the df. So what would be the dynamics of
partial f by partial?
So it's going to be partial f by partial t t plus partial f by dx and partial, for example, f by partial t2 plus 1/2 also, right? Plus 1/2 partial f by partial t2 dt. Okay. partial d partial x dt dwt, right? And plus 1/2. Okay. Yes. Plus 1/2 partial 2f by partial x2 and dx square, right?
सही है
F C22 में है.
Sorry?
F C22 में.
We can assume C22. Okay. We may assume that. Okay, let's assume that now f is from C2 class. Okay, so it's both derivatives exist.
There is mentioned about what
I'm saying the differential. So it's about what, if I want to write about what, then I have to write it in integral format. Okay, so this is what is going to be the differential. Alright, so now I'm gonna assume, so I'm gonna write many things in corrective form. So I'm gonna write an Ito rule table actually. I'm gonna try to explain that, what do I mean by that. So if you're gonna multiply, so I have a dt and dwt, okay, dt and dwt. We're gonna ignore the higher order terms of time than first order terms. So what will be dt dt then? What will be dt dt? That will be 0. So if I don't want to keep the higher order terms, more order terms than first order, then this must be 0. What will be the order of dt dwt? So here's an explicit meaning of it. So when I'm multiplying dt dwt, what do I mean by that actually? So I think I shouldn't write a dwt but a dxt here. I think take dx, simply dx, not dwt. I'm writing it. dx होना चाहिए. तो छोरो आप भी सो रहे हैं.
1/2 भी एक और भी तो करना है.
So now let's think about dt dwt. Now I want to interpret this in the terms. So by dt I'm going to mean some increment, w of t minus w of s. Okay, some really small increment. Okay, where s and t are really close to each other, and by dt I'm going to mean t minus s. Okay. Question is, what would be the distribution of this function? So the mean is going to be 0 for sure. What would be the variance? It's normally distributed.
T minus
So it's going to be t minus s square actually.
टाइम्स t minus s
Okay.
भी होगा.
t minus q हो जाएगा ना सर?
क्यूब हो जाएगा.
T minus s whole cube.
T
t minus s no
होना चाहिए.
Square होगा.
that's square, that's scalar term, so it would be square of this.
इसको ऐसा करते हैं. So let's think from this perspective. So I know that if I have Brownian motion, w of t minus w of f square, okay, in L2 omega sense is approximately t minus s. Okay, in other words, its expectation is t minus s. Okay, so I'm gonna, in a cryptic language, I'm gonna write this statement as that the square of dwt is approximately d. So that's a cryptic way of writing it. So I'm going to write this, but I'm going to mean this actually.
सही है सर.
Okay? I'm going to write this, but I'm going to mean this. Okay, ji? So you have it. And now, what does this mean? So what would be the order of this term?
3.
What would be the order of this term?
3.
So dt, and what is the order of d2?
1/2.
So it's going to be dt 3/2 actually, right? So 1 plus 1/2, because dwt square is dt, so the dwt is going to be the square root of dt. So the order of this term is going to be more than 1. So if it is more than 1, 0. Not interested in that term. And what would be dwt dwt? Let's say it's dt. Okay.
Sir, ये ना
And
sir ये और dt थी.
so this would
by
be
ये
0.
zero और ये
Yeah.
zero.
As I'm saying, the derivations that I am doing here are heuristic in its nature actually. So they are not rigorous. Okay? You can prove them rigorously, but that would be a lot of time. And now I want to do what? In this expansion, wherever you have x, just replace xt. Replace xt. So when you're gonna have df dxt, so what you're gonna get? You're going to get partial f by partial t, okay? dt plus partial f by partial x dxt. You may assume that you are doing the evaluations at dxt. So you are differentiating first with respect to x and then you are substituting txt. Okay, so that's what. So dxt plus what would be this term? So this will go away. I'm not interested in it. Okay. How about this term? So it's going to survive. Some part of it is going to survive. Why? Because if I have 1/2 partial 2f by partial x2, and I have dt dxt, and plus I have 1/2 partial 2f by partial x2, and I have dxt square. So this term will go away, the rest of terms will survive. And now let's write it more explicitly. So if your dxt is this mu dt plus sigma dwt, then what term will survive from here? So in other words, substitute the value of dxt here. So we're gonna have. We're gonna have. Okay. So
कोई भी नहीं survive करेगा.
करेगी ना survive. ये पहली term करेगी ना बेटा. Because you have this dt here.
फिर dt square खत्म करो.
नहीं. Okay.
ये वाली zero हो जाएगी. ये dxt square हो जाएगी.
जो ये नीचे है ना dx.
Okay. So this will also go.
Yes, sir. Yes.
This will also go.
ये
last term will
जो square है ना उसका ग्रामार के बारे में.
Yes, the last term will survive.
dt square हो जाएगी.
नहीं dt square नहीं होगा ना. It's a dxt का square.
Stochastic process, not
It's a dxt square. So when you're gonna simplify this, you're gonna have what? You're gonna have what? So you're gonna have your dftxt is going to be equal to this partial f by partial t dt plus partial f by partial x dxt. But if I wish, I can substitute this mu dt plus sigma dwt, right? So I can substitute it here plus 1/2 partial 2f by partial x2 of what you're going to have. So we're going to square this.
Sigma
So the first term will go away
dt.
and the middle term, twice term will go away. The only last term will survive. So we're going to have what? So the sigma square and dt. Right? So if you combine all these terms, in other words, write this process dxt in its Ito form actually. So you're going to have what? You're going to have 3 terms, right? There's going to be partial f by partial t and mu partial f by partial x plus 1/2 or maybe the sigma square over 2 partial 2f by partial x to dt plus okay, sigma partial f by partial x and dw. So this would be the dynamics of a function of an Ito process. This is called the generalized Ito lemma. So that's a generalized Ito lemma. Okay? Generalized Ito lemma. So where we're going to have generalized Ito lemma? We're going to apply generalized Ito lemma in those situations where I have an Ito process that satisfies the stochastic differential equation. And then you're going to say that what is the dynamics of a function of stochastic differential, function of that Ito process. Okay? So you have to keep in view that when you want to compute this, you not only have to compute these partial derivatives, but you also have to take care of this mu and sigma. So these two are not in your simple form. So from where you're going to have mu and sigma? So that in the stochastic differential equation of xt, the mu is the drift and sigma is the diffusion actually. Okay?
They will be given to us.
They will be given to you. There will be some function. So you just need to substitute and find the dynamics of it. Right? So it's really the heuristic derivation of it. Let's do one example. And this example is important. You have to keep it in your head always. And you have to keep in view that this is true for f in calligraphic L2AD in general. So it's true in L2AB, it's true in L2AD, it's true in calligraphic L2AD. So it's a pretty general truth. Okay, so I haven't proved it. So I just have a heuristic derived it. It's like proving by magic actually. It's not really a proof. Okay? But for now, it's enough. Okay. So here's an example. So imagine I have an f from L2, calligraphic L2AB. Okay, this is space. And I say that xt, the dynamics of xt looks like this. dxt minus 1/2 f square of t dt plus what? F of t dw. Okay, so I have this process. It's written in integral form here, but I have written in differential form. It's the same thing. And I want to know that imagine I have a function this. F tx is e to the x. In other words, I want to know the dynamics of e to the xt, exponential of xt. What would be the stochastic differential equation satisfied by the dynamics of d of e to this process actually. Okay? So what you're going to do, so what would be the dynamics of this d of e to the xt? A time will come when we'll see that this is really, not important. You can always have a Taylor expansion of things. Whatever the differential equation is given to you, just Taylor expand it and substitute your dxt here. And just drive. So there is no need to memorize this Ito lemma actually. You wish you can keep it. But for example, if I have to drive the dynamics of this, so I'm not gonna, if I wish I can use this SDE and this Ito lemma, but if I wish I can directly drive it actually. I can directly say that this is going to be. Anyway, so can you compute it for yourself? Would that be difficult? So the mu is this 1/2 f square of t, and this is your sigma of t. So just substitute things and And so you just have to take ftx equal to e to the x, simple x, where your x
So
cryptically
these both
means
f are
x.
different, right? This
Sorry?
f is the f square thing is different and f tfx is
No.
they are different.
Okay, yes. Oh yes. Let's give it a name then other gf. Yes, this is the good one. Okay? So let's substitute values in between there.
Limit of 0, limit of is same.
Another example is, imagine you have a bird or a particle, okay? It's called the Langmuir equation. It satisfies the Langmuir equation. Its velocity satisfies the Langmuir equation. The dxt equal to minus beta xt dt plus alpha okay. This is called Langmuir equation. Okay. I mean, if you for example just look at this equation, so in deterministic sense this looks very familiar actually. Okay? Where beta and alpha are numbers obviously. So this looks very familiar. So this kind of represents that, okay, you know, and is beta positive? Yes, beta is also positive. So what does this would represent? So it's a deterministic equation simply saying that if xt is the velocity of the bird or particle, so what does this simply say? That the velocity is exponentially going down. Okay? And now you are saying that no, it's exponentially going down, but there is another forcing factor, that is a random forcing factor. You know, maybe air or something else. Maybe the other birds are colliding with it. Maybe something crazy is happening with it. So it's really creating the hindrance in this decay. The question is, what would be the velocity of the particle? And what will be the velocity of the, what do you call this bird actually? So what you have to do, you just have to solve this equation. Okay. And this is a linear equation actually. Isn't it? It's a linear equation. Why linear? Because you also have a linear stochastic differential equation. So if the process or the differential equation depends on the first power of the process, we're going to call it a linear differential equation. There isn't anything that creates trouble. So how does the, what is the kind of the solution for example, linear differential equation? What is the nature of solution of linear differential equation? No matter what order you have. So you can always write in the terms of exponentials. Okay. If you remember, first order, higher order differential equation, if it is linear, you can always write it in the terms of exponential. So since this is linear, so maybe it has a solution of what do you call exponential format. Okay? And the answer is yes, it has this solution. Suppose you can verify, I'm leaving this for you. You can verify that if you apply the lemma, for example, on this e to the beta of tx, okay? In other words, if you in other words, I'm claiming that this is really the solution of a stochastic equation.
सर इस पे अप्लाई करेंगे लेकिन x of t हमें फाइंड करना है सॉल्यूशन x of t
फाइंड करना है I'm going to apply so मैं करूंगा ऐसे I'm going to apply into lemma on this guy and then I'm going to divide everything by e to the beta t. So what I'm going to have is only x actually, and x is xt. So that's a trick. I have the solution. So in the next discussion, we're going to talk about how to solve linear differential equation like we solve in differential equation. So that will be our next problem. Okay, so if you apply the lemma on this, what are you going to get? So let's do it quickly. Partial f by partial t is going to be the beta e to the beta t x, in other words beta f, right? So it's really simply beta f, and what would be partial f by partial x? I'm sorry?
Beta xf.